Good morning, everybody. Today, in our topic, we shall discuss about energy stored in a charge capacitor. So, again, I shall repeat the topic. Today, we are going to discuss energy stored in a charge capacitor. Let's imagine a capacitor at t equal to 0. It is not connected to a battery. Then, initially, it has no charge and no potential difference. In order to store energy on a capacitor, we need to do work, and this work is stored in the form of electrical energy. So it can be written as the work done in charging a capacitor is stored in the form of electric energy. So the work transforms itself into energy, that is electrical energy. So we'll consider a capacitor having capacitance C, and on being connected to a battery, let after some time t equal to t, it develops a potential V, and when it develops a potential V, let assume that q amount of charge has been accumulated q on each of the plate, and the expression for charge which has been accumulated on the plate will be given by q equal to cv. Now suppose that the battery supplies small amount of charge dq for time t dt at constant potential V. So interesting line. Suppose we keep on supplying charge dq from the battery without changing the potential of the battery, which is maintained at V. Then amount of work done by the battery will be given as dw is equal to V dq. So we know that from this expression, from this above equation, we can write V as q by c. So the equation becomes q by c dq. So what we have done here, we have supplied additional charge dq, keeping the potential of the plate same. So for that we need to do work, and this work is expressed as V dq, and substituting the value for V from above equation, we get q by c dq. But our target is to charge the capacitor from 0 to q. Initially it has 0 charge, and finally we wish to charge the capacitor which will have charge as q. For that we need to integrate. So total work done in charging the capacitor from 0 to q is given as w is equal to integration of dw. So from above equation dw happens to be q by c dq, and the limit of integration will be from 0 to q. So we see that 1 by c is common, so we are left with this term, and the integration of this happens to be 1 by c q square by 2 upper limit lower limit will be included. So q is the lower limit, 0 is the lower limit, q is the upper limit. So simplifying this one, we get 1 by c q square by 2 minus 0. So this expression becomes w is equal to 1 by 2 c q square. So this is can be written as w is equal to half q square by c. Also we know that q is equal to cv. So this can be expressed as half cv square by c. On further simplification, we get half c squared v square by c. This gets cancelled, so we get half cv squared. So these are the two final expression we are giving. Again if we substitute for cs q by v, then the above equation which we got, w is equal to 1 by 2 q square c will become 1 by 2 q square, here q square by v. So this will take the expression as 1 by 2, this gets cancelled, so q v, half qv. So this all work done which we have expressed it here will be stored in the form of electrical energy, which is expressed by U. So we have expression now as 1 by 2 q square c. Also we had equal to 1 by 2 cv square. Also just now we have proved 1 by 2 qv. So these are all expression for energy stored in a capacitor, having different terms, one in respect to q and c, other we are having in respect to c and v, and other we are having in respect of q by v, which will be required for solving the numerical when different given quantity will be there in the numerical. So today what we have discussed, let's revise it a bit. We have discussed about energy stored in a charge capacitor. As we know that energy stored in a charge capacitor is done by doing work, and whatever work we do by whatever work is done by the battery will be stored in the form of electric energy. So initially we imagine that there is no charge on the capacitor. So when there is no charge, there will be no potential difference. Say we connect the capacitor with a battery, then after some time, let the potential difference between the two plates becomes V. So when the potential difference between the two plates becomes V, means it has accumulated, the plates of capacitor has accumulated some charge on it, and this charge is expressed as q equal to cv. So from this we will go a step ahead. We will wish to send another dq charge, keeping the potential of the plate constant at v. So we will require to do some additional work, and this additional work is given as v dq. So substituting the value of v from above equation, we get q by c dq. But our target is to charge the capacitor which was having initially 0 charge to charge q. So we need to do work, and the expression for work is given as w equal to integration of all small dw's. So simplifying we get w is equal to q square by 2c. So this is the work done. This much work done is required to charge the capacitor to a charge of q on each plate. but we can have different expression for work done by substituting the values using q equal to cv. So we get three terms, that is half q square by c, or in terms of cv we get half cv square, and it can be also half qv. So these are all the expression for energy stored in a capacitor. We did work, and this work is stored in the form of electrical energy, which is expressed by the term u. Thank you.